Conversations about cleaning up our environment and reducing carbon emissions have dominated much of global dialogue over the past decades. Many countries have made substantial progress in cleaning up their footprint, but there still remains an incredible amount of work to be done. The world still produces upwards of 37 billion tons of carbon every single year, and that number is growing. Transportation and mobility make up about 1/4 of all of these emissions, and that will be a huge part of the challenge that the world faces over the coming decades. But it will also be one of the biggest opportunities for us to make substantial impact across the world. Road transport, or cars, vans, trucks, buses, and similar, make up around 3/4 of transportation emissions. And around 95% of that activity is still fully fueled by fossil fuels. We see electric vehicles as one of the biggest possible opportunities to help solve this pressing challenge over the coming years. We're currently at around ground zero for electric vehicle adoption across the world, but massive growth is expected over the next several decades. Somewhere around 700 million EVs driving around on global roads by 2050. This is a huge amount of EV adoption. One of the biggest reasons that people are skeptical about adopting an EV remains that there is a lack of confidence in charging infrastructure. If you're not sure where and when you'll be able to plug in your vehicle to continue driving around, you will feel less confident about adopting a new EV. In order to support these massive numbers of EV adoption that we're expecting over the next several decades, there also needs to be a huge deployment of charging infrastructure. While much of this can be taking place in people's garages or driveways at home overnight at slow rates, some of this needs to be in public and distributed. Some people may not have access to garages or driveways. Maybe you're a business and you're trying to optimize your logistics efficiency, and you need to have your drivers on the road all the time, constantly. All of this means that public and distributed infrastructure is absolutely critical moving forward. And a big part of this is also the shift towards faster and faster charging rates. It used to be that you would plug your vehicle in and have to wait around for many hours to get a full recharge. The speeds are increasing drastically every single year. Some of the fastest chargers available today are right around 350 kilowatts and can recharge an average EV in just about 10 minutes. In order to reach this level of speed, though, the amount of power required is absolutely massive, 350 kilowatts. Just to put that into perspective, if you take just 8 of these level 3 350 kilowatt chargers and put them in one place, you end up drawing more power than from a 1 million square foot office space. This is an absolutely massive amount of power draw. Now start thinking about things like electric delivery vans, semi-trucks, heavy industrial machinery like tractors. All of these can sometimes charge at even higher power rates, something on the order of 1 to 2 megawatts for some of the more recent standards. That makes this challenge even more complicated and harder. Beyond all of that, the actual process for getting a charging station installed today is complicated. You can see many of the steps listed on the screen here. You have to do things like work with the permitting bodies and local utility companies to get relevant permits, to sit through long interconnection queues that can sometimes last up to several years. You might have to work with them to tear up streets to install new high-voltage distribution lines. These activities are very expensive and also very disruptive to local traffic in the area. You may also need to order new equipment, like high-voltage step-down transformers. These pieces of equipment have lead times that can reach upwards of multiple years at this point in time. And finally, when you get the station installed, operating it doesn't always turn out like the project operator intended. This is where my company, Revterra, comes in. We want to help you install the next generation of fast EV charging stations without going through any of the hurdles that I listed on that past screen. We can help you utilize the existing electrical infrastructure in place, typically a lower power, and use our battery system to boost and install brand new, high-speed EV charging, regardless of the grid conditions where you're currently trying to install that project. Our battery system acts as a buffer, taking in continuous low power from the existing grid interconnection and then distributing that power at very high speeds when cars come in and plug at the station. We transform what would otherwise be a very spiky and variable demand profile from an EV charging station into a very smooth and continuous power draw. This increases drastically the stability of the surrounding electric grid and also makes it more profitable for operators in areas where there are things like demand charges. Revterra's battery system is this white cylinder that you can see in the screen here. This battery system can work with any type of incoming power. From what I've discussed so far, I've been talking about using existing grid connections. We can also help you install an EV charging station fully off-grid by utilizing things like local solar panels, wind, or just about anything else that the customer might be interested in. We're also able to work with any type of charging dispenser, any power level, and any of the major manufacturers. We are all about making the customer's EV charging work exactly like they need it to. Our S100 kinetic battery system is shown on the top right here. You'll probably notice that this looks quite a bit different than any battery system you're familiar with. That's because this battery is a fully mechanical battery system, fully non-chemical. We actually use motion itself to store energy. How exactly does that work? Well, we take energy from the grid, local solar panels, or just about anything else, and we use that to turn an electric motor, which spins up a very heavy steel mass. This mass spins faster and faster the more energy you put in, and then when a car comes to plug in at the station, we slow it down and reverse that process. Very simple physical process, but fundamentally completely different than most chemical battery systems. Each one of these batteries is roughly 2 meters in diameter and about 2 meters tall. They can store 100 kilowatt hours of energy and can output about 800 kilowatts at a maximum continuous rate. This is enough to feed 2 of the fastest EV chargers available for passenger vehicles today. All of this is made possible by Revterra's breakthroughs in bearing design. We have a passively stable magnetic bearing that enables this system to operate incredibly efficiently, right around 20 times more efficient than previous kinetic energy storage alternatives. We have 3 existing patents protecting the technology, with several more on the way as we continue to improve and give a better offering to our customers. As I was saying, we are ultimately flexible to meet the customer wherever they need to for this EV charging goal. We can work with any level of power interconnection coming in, and we can work with any power level of dispenser going out. We can even expand this to do things like feed semi-trucks or heavy industrial machinery by putting multiple of our modules in one place. Whenever the customer has a power bottleneck or a need solved to install their EV charging or mobility goals, Revterra can help. The grid is fundamentally an alternating current basis system because traditional generators like gas and coal turbines actually rotate as they combust fuel in order to maintain the frequency on the grid. Most battery systems, however, are fully direct current or DC based. This means that in order for those 2 pieces of equipment to play nice with the grid, you often need to introduce new power electronics like inverters and converters to get from AC to DC back to AC to make the power usable. This becomes a huge issue sometimes because those power electronics can be very costly, but beyond that, they can also be very failure prone. Particularly when we're trying to build up EV charging infrastructure that is hugely reliable and can convince customers to switch, reliability is absolutely key in these markets. Revterra's battery is fundamentally different. Because it's a rotating piece of machinery, it is actually an AC native frequency synchronous device. That means we can actually fully eliminate the power electronics typically required to do an EV charging installation like this. No inverters and no converters. This means we can help customers save cost on the installation, but even more importantly, increase the reliability of the project substantially. You can be confident that your EV charging station will be up and running whenever you need it. Our battery system is also very environmentally friendly and has a completely decoupled supply chain from traditional battery systems. This battery is made almost entirely out of steel, and as we go to build more and more of these battery systems, we will source all of that steel recycled. That also means that when the battery's long life is over, it is once again fully recyclable. This gives us an almost entirely circular environmental footprint for this battery and is also, as I mentioned, quite different from what traditional chemical batteries look like. For any components that are not recyclable, they're very safe and easy to dispose of. We don't directly use any chemicals like lithium, nickel, cobalt, or otherwise. The image on the right shows our existing supply chain in blue for where Revterra currently produces batteries in our Houston, Texas headquarters location. The yellow locations show where typical inputs for chemical batteries might come from across the world. As I mentioned, our supply chain is completely different. For now, as we build batteries in the US, we can source almost everything domestically. In the future, as we go to build more of these and sell to markets in Europe or otherwise, we can do the same exact thing and localize manufacturing in those areas. This should help us provide a supply chain that is much more robust and less exposed to geopolitical risk than traditional chemical batteries. The battery also lasts an incredibly long time. Most chemical batteries last for something on the order of 3,500 cycles to 7,500 cycles. Our battery lasts for upwards of 40,000 full depth of discharge cycles. In practice, the graph on the left shows 5 cycles per day, something that we expect might be reasonable for an EV charging installation. On a 5 cycles per day cadence, our battery lasts for more than 20 years, where chemical batteries might need to be replaced about 8 times throughout that same time period. That could be incredibly costly because replacing those cells every few years incurs a huge capital expense up front, but it's also very challenging operationally. You might have to shut the site down frequently to maintain and install these new cells. Beyond that, chemical batteries suffer from degradation issues. Oftentimes, it's quite hard to predict what capacity of power and energy will be left in the system after you're done using it. This can be exacerbated by tough environmental conditions and otherwise. It also gets worse when you push more power from the cells. Our battery, however, does not degrade at all. 20 years down the line, it still has exactly the same energy and power capacity as it did on day one. This means you can be much more confident about the project that you've installed and also increase your profitability by not having to overbuild the capacity up front. And we're not just stopping with EV charging either. We can do many other mobility applications. For example, high-powered pulse to support electrified train travel. We can help you recapture energy as a train breaks into the station and then quickly reuse that to push the next train leaving the station. We can also do things like provide critical industrial and commercial backup power at sites in a way that is substantially faster than existing UPS solutions. Because our rotating device operates grid frequency synchronous, we can actually provide backup power physically instantaneously. This means you don't need to wait the 15 to 20 milliseconds typically associated with backup power devices. We can also offer physical grid inertia, which will be absolutely critical as renewable sources like solar and wind start to replace coal and gas turbines even more across global grids. In the future, we also intend to help with things like peak shifting and energy arbitrage in long-duration storage markets. All in all, if a customer has any energy or power bottleneck in their operations, Revterra can absolutely help them solve that. Here's a quick timeline of the company's development, and I'll hit a few of the highlights here. The company was formed in 2017 with the issuance of our first patent, and we spent the next several years developing several prototypes of this technology. In 2022, we raised a Series A in order to fund the deployment of our very first couple of commercial projects. The first commercial project with our very first paying customer will be going into the ground over the next few months in the US. In 2025 and beyond, we hope to expand our manufacturing and commercialization substantially and start offering product in Europe and beyond. We want to help customers start solving these critical issues that I was describing as soon as humanly possible. I'm Patrick Flam, the CFO of Revterra, and you can see several of my other leadership team members up on the screen here. We also have a great list of commercial partners and also funders. If you're interested in exploring how you might be able to collaborate with us into the future, or if your company might be able to benefit from using our technology in your operations, please come and speak to me after this presentation. I really appreciate the time today. Thank you.